All right, so okay, I think that so in last the hour, we try to convince you that how can plasma can change that the low temperature chemistry, how that they can accelerate flames and flame stabilization using plasma assisted, ignition assisted flames. And now I try to give you answer that how plasma can minimize the ignition energy and in a mixture. So yesterday we talked some of the phenomena. This really does not work. It's really dead. It does not work, really work. Let me change it back. So yesterday we show you some of the experiment in this kind of UAV engines, and you put a microwave into it. You can enhance that the operation ignition limit or minimum ignition energy for the engine to operate at a few NIN conditions. And and this is a very important typically for gas turbine engine. If you have aircraft and that can fly very high, and you will see that this is the attitude. When you fly high altitude, you find that the ignition sometimes is failed. That is typically a problem for military engines. Sometimes they want to fly very high, but when they fly high, the igniter, they cannot ignite in the afterburner. So, and the people always say that this is because the flame speed is low, and then we cannot. But if everybody in combustion, we understand the flame speed is proportional to N divided by 2. N is the reaction order, minus 1. N is typically to less than 2. In that case, that in hydrocarbon fuels, like jet fuels, that higher the pressure, the flame speed go down a lot. In other words, the lower the pressure, the flame speed increase a lot. But why would that the flame speed increase at high altitude? The flame becomes blow off, blow away. Right? You cannot explain it by flame speed. So this is something, when I came to Princeton, I look at it, I say that, well, this is very interesting. Every time you have a controversy, and every time you have opportunity, and what do you want to do? So if you're looking at a combustion book, and there's one thing they call minimum ignition energy, and people always try to say minimum ignition energy is that you create a kernel, that kernel size equal to the flame size, then they will go by itself. If you look at the Professor Irv Glassman's book, maybe they just say that. And if you learn flame dynamics, you know there's something called Lewis number. I talked before, it's thermal diffusivity, mass diffusivity. And many of the book, like Bernard Lewis, Peroni, Irv Glassman, they say, okay, minimum ignition energy is proportional to, you have to create a size of spark as a flame thickness, and then multiply by the enthalpy, and because the flame has to be at the bed temperature. And this is that minimum ignition energy. And then you put it into a flame speed that inverts to the flame speed to cubic, that is inverts to the Lewis number. This formulation is very questionable because when you have a large, everybody knows that when you go to jet fuel with heavy large molecules, the Lewis number is large. If you say Lewis number is large, minimum ignition energy is lower, that's contradictory to the experiment. Everybody knows that when the molecular size is increasing, the Lewis number is increasing, ignition becomes difficult. And certainly this is wrong. And what is the right one? And you have a famous theoretician, Zeldovich, and he said that ignition energy is not by flame thickness, it's by something called flame ball. And the flame ball, how many people know flame ball in this room? None of you. Wow. And, but if you have a homogeneous mixture, you spark it and you generate a flame. The flame, let's say you generate by magic, you generate this size of flames. What happens? The flame either go out or they collapse. There's no way they can improve this flame, they can stabilize it like this, right? No one really observed it before the theories say it might be exist. And theoretically, if you adiabatic flame, and Zildovich says that this is flame ball. The flame ball either collapses inside or expanding outside. And your ignition energy has to be equal to generate a spark as the flame ball size that they can go this, because flame ball is spherical. But no one can observe flame ball until this gentleman and Paul Roney did experiment in microgravity. And he put a very lean hydrogen mixture and in microgravity, and he sparked it, and he found it, oh, there's a hydrogen ball, stay there like a ping pong. You just stay there forever, forever. That's for the first time that people observed a flame ball in microgravity. And he could not explain it. But a theoretician called Buckmaster. Do you know Buckmaster? Oh, you don't know. You know. Good. That's you know combustion history in theoretician. Buckmaster was a wonderful applied mathematician. And he said that only radiation can stabilize the flame. If you adiabatic, flame ball never can be stabilized. Because when you have a flame try to propagate outside, the burning gas volume is going to increase. The radiation say, oh, I got too much heat losses, and you come back. See? This stabilize. Radiation stabilize the flame ball, right? When the flame ball try to shrink, and then the radiation gets lost, getting smaller, and the flame getting stronger, there was, oh, flame, you come back. See what I'm saying? How radiation change a lot of combustion phenomena. So this is a flame ball. And that say the proportional Lewis number, they are contradictory. So what is right? These are famous people, and if you look at their names. But God probably can only have one answer, right? Either is wrong or none of them are correct, right? So at that time, I see the opportunity. Now I try to ask my student at Chen, and when I came to Princeton at that time, I say to do a theory that you write down and study flame propagation as time-dependent convection, diffusion, heat losses, radiation, reaction, and you solve it. And when he come back and talk to me that, well, here is that the flame temperature as a function of ignition power, as a Lewis number, as a flame radius, at flame speed is activation energy is expressed by this equation. And then you plot that one, I showed you yesterday, is basically say if Lewis number equal to 1, if there's no heat losses, and you can see that the ignition power, small flame die, ignition power is increasing, you have a minimum energy, and then suddenly the flame will accelerate by itself. This radius, even at the Lewis number larger than 1, you can see this radius is what I call flame radius, minimum flame radius. So the spark has to overcome this minimum flame radius, and before they can propagate by itself. And so this is that the flame ball. And you can see that the flame propagating speed as a function of radius. Then when the speed goes 0, this is the flame ball. The flame ball is somewhere here. The minimum critical radius is somewhere here. It's slightly bigger than flame ball. But if you plot that so I don't need to do this. Is too lot of things to do. If you plot that the minimum ignition energy, and you plot the cubic of the radius of critical radius, and at a different Lewis number, you can see that beautifully they fall on the same curve. Direct numerical simulation compared to the theory, they say the same thing, saying that the minimum ignition energy is governed by the critical radius. And then for a certain activation energy, they are on the curve. Another activation energy is this. So this was a earlier work, and I present this to Air Force Program Manager Tishkov. He said, wow, this is wonderful. That really helped us to understand how do you enhance ignition energy. So then he gave me funding to measure what is a critical radius and what is as a function of equivalence ratio. Now I look at this is JP8, is that jet fuel, And this is that the synthetic paraffinic kerosene. So this is that fuel. You can see that this is atmospheric pressure. At 1 atmospheric pressure, that the critical radius reach to 2 centimeters, this size. And the leaner the mixture, the critical radius is bigger. Now you understand why that the lean burn engine is so difficult to ignite, because the critical radius increase. So now you also understand this is that the flame rate is normalized by the flame thickness. At low pressure, flame thickness increase. With when you decrease the pressure, the critical radius even more increase. So that's why that aircraft, they cannot be ignited when you fly altitude. It's not because of flame speed. It's because the critical ignition radius, flame radius, they increase linearly with the pressure. Do you understand? So this, I tell you again, that how that you learn combustion at chemistry, but the physics, but also theory, are also important to tell you something you really don't know and for calculate. So now you really understand. Now I try, can we do experiment? So here's the experiment. I have a methane mixture. I'm using 1 spark. You know, this is a very electrode. And put the energy, and you can see I spark it, and the die. So now I split the energy. I put the electrode 1, 2, 3, 4. You have 4 electrodes. Once you put the voltage between the first one and the last one, if there's a spark current generated, they become a conductor. And the voltage drop to the next one, and the next one by one, they just ignite it in a row, right? You have, if you put a 4 metal, if you put the voltage between the first one and the last one, when the first 2, they arc, then resistance goes to 0, and then the voltage drop the next one by one, they just ignite. This is just like, I call it a cascading spark. And I put the same energy in the mixing, you can see that I increase the volume, and I can ignite. So now that the people started that, how do I ignite a lean mixture? Create a big spark using cascading, using multi-spark, or using whatever corona you can do, and gliding arc. That's the beauty of theory and the experiment. Now my former student, what is Tim Mermello, I said, what if that you have flow? I have he has a wind tunnel, he have flow, and then he have so how does the flow affect that? And he measured that the flame, a spark, and it's a different 300 kilohertz or whatever. You can see that it was a low frequency, and then you have an individual kernel, a high frequency, and all these kernels are coupled, and the flame is easy to be ignited. You can see this video, and at a high frequency, and then your big flame kernel is formed because of high frequency. At low frequency, you only have 1 by 1. So that you can enable you using that frequency. Then adjust the gap of the electrode and see how that with the flow, how that ignition probability. So this is that when the gap is very small, I think that what is the 1 millimeter, you start to see that the ignition can only happen between 0.8 to 1. When you increase the gap, and you put 1.5, you can see that they can linear and linear and linear and linear. So again, it says that the spark size dictate that whether ignition can be successful. Even the mixture is flammable, right? So this is something. I come to GE, I try to convince them to think about this. They're probably very difficult to convince GE to understand this. I think American industry needs to engage more with academia to understand what is the new technology is going on, particularly Boeing, and it's horrible. So by the way, I was at the AIA meeting. I was elected AIA fellow. I ran into three of them from Boeing. They were elected fellow. I was telling them, guys, that you have to understand the quality and the excellence, safety are the most important things in. Right? It's not just the profit or it's just something else. So I think that some of the Boeing create a lot of problems. Particularly, you see that the spaceship, they're flying to the United States. They cannot come back now because they have problem in their spacecraft, right? It's all Boeing created this kind of mess. So they are not really trying to develop high quality, high something. They don't have the spirit to become a professional, to develop something they're proud of it. they lost their soul in terms of, this is the industry. I think that, it really disappointed me a lot. So, and again, so you can use in the gap and to change the spark size. You can also use in the repetitive discharge in your flow to control the size. So this is how that the experiment basically is showing how that you a different kind of a number of pulses, and how do the minimum ignition energy decrease with the number of pulses, because that you create a bigger ignition kernel size. So this is that, again, is that the experimental data about that what is a different, very beautiful data about this, the OH PLF, and finally see at a different frequency. And this is the frequency, this is at what, time. They can see that at a high frequency, you can see a lot of spark formation. So we basically committed the computation and of this thing, and basically show a similar result will happen. Another thing that is, for example, in a scramjet engine, for example, is ethylene injected into the cavity, and if you're looking at the flames, and the flames spread in the cavity, and if you're taking that as the formaldehyde image, a lot of formaldehyde is formed. What does it mean? That means a lot of intermediate temperature reactions are going on in the cavity, so that dramatically enhances the ignition process. So this is another figure and given to me by Professor Mastrakos, and in Combustion summer school. And what he said that the flame stabilization is an open environment and they close the chamber. And what the phenomenon he just said that when the OH and formaldehyde, and then so if you're looking at the flames and near the extinction, they start to see a lot of far from lean blow-off, close to lean blow-off. There's a little formaldehyde is formed here. There's a lot of formaldehyde from here. If the formaldehyde is here, that means that is a lot of low temperature chemistry. The high temperature chemistry start to die, and the low intermediate temperature chemistry start to dictate. And then that's the time that the plasma can help. You know what I'm saying? So this is experiment data. Then in somebody else, again, to see something is interesting. So now come back to show again the theory that if you have a cavity and enhanced combustion, this plasma assisted ignition, assisted flame propagation will help you stabilize the flame. And then the key question is, how do you generate a big volume of plasma, right? That is something, and we just got a contract from Navy and to try to develop this kind of a concept to enhance that the UAVs flame stabilization. We'll see how it goes. So if this is true, is plasma enhanced low temperature chemistry can enhance ignition assisted flame speed? Why not in a turbulent flames that if you can enhance, for example, low temperature chemistry, for example, then you can enhance turbulent flame speed. So a lot of people in turbulent flames measure turbulent flame speed, normalize or nominal flame speed as a function of turbulence. The only thing they measure is this curve for methane, for whatever, a lot of same people. But for me, I'm interested in the low temperature chemistry. When the Dunker number of low temperature chemistry is bigger than 0, and then I find in the laboratory, this is that when you have a 0 low temperature chemistry, this one is you have a low temperature chemistry. You can see the turbulent flame speed can be anywhere between. So, right, what is turbulent flame speed? A lot of people are measuring. For high temperature, is well defined. When you have a low temperature chemistry going on, a lot of low temperature chemistry is going, ignition is going on, then turbulent flame speed is poorly defined. And many people just don't understand this. I mean, try to keep measuring a lot of things. But also, and this is that they show you a video, and maybe you will play or we may not play. I don't know whether you play or not, so it does not play. Basically, it says that when you trigger low temperature ignition, the flame flashback, that is, the flame speed increase a lot because of ignition assisted flame speed. So now the next thing, try to detonation. Detonation becomes a very hot topic. That if you, this is that the Hoganute curve saying that you have a Chapman-Duguay detonation, you have deflagration. And then a flame can come from here to here. This is the ZND structure, and you have a shock wave, have high temperature, subsonic flow, and ignition happening, combustion happening, and the flame reach to sonic speed, and the whole structure propagate to CJ velocity. And CJ velocity is a function of heat release and gamma. That's it. Once you give me heat release, give me gamma, my velocity is determined. Very simple. But the question is, look at this diagram. This is the flame. This is detonation. How does this from here to here, how does it get there? Anyone in the combustion class tell you how that this point, from this point to that point, how does it go? Go from here, go from there, or go from where? Why does it fail? Has anybody tell you in combustion class how the flame from this diagram, they go there dynamically? Have you heard anyone? Let me know if anyone raise their hand. No one, right? So this is a problem about the combustion. You know, see what I'm saying? And people, a lot of people look at this diagram, they actually don't know how that the DDT is really happening on this diagram, right? So DDT, what is the mechanism? There are a lot of people saying different things. There are people, particularly the turbulent group, they believe that if you generate a turbulence, the turbulent flame speed is increasing. Eventually, when the flame speed is larger than CJ velocity, they detonate. I don't believe this theory. I don't believe it, okay? And then the second thing that you have a hot spot and you have a gradient. This is Zeldovich theory. You say that you have a hot spot. In the hot spot, there's a gradient. All the ignition happening at somewhere, and then because of the gradient, then there's another ignition happening, one ignition catch up, another one, eventually form a supersonic ignition wave that get into ignition. That makes a lot of sense. And another theory that people call gradient. Remember when people doing DDT, people always need to put a barrier, put a spire inside the tube. So they say, okay, we generate turbulence. Yes, it generates turbulence to enhance flame speed, which is true. But more importantly, it generates friction. That heat release will couple with pressure. That pressure gradient help you to develop DDT. So there's a lot of papers on this, and let's see that Zeldovich gradient theory. It basically said if we have a temperature gradient or concentration gradient, the ignition delay time and is a function of temperature. If you take that temperature gradient, you have ignition gradient. If the ignition gradient is like a speed of ignition wave, if that speed is close to the sonic speed, then you start to couple, because my ignition speed is sort to a sonic speed. They say that if this non-dimensional number equal to 1, detonation could happen. If it's lower than 1, larger than 1 is spontaneous ignition, is larger than 1 is deflagration. But one more condition is that Bradley in UK, and they define that not only you have to have ignition speed is fast. For example, very lean mixtures, they never detonate. Ignition can be fast, but never detonate. And he proposed something like, okay, that the time of combustion in a flame thickness, that's delta divided by the velocity, that has to be greater than the sonic speed. In other words, the heat release generated in the combustion zone is faster than the acoustic speed. That means that the acoustic cannot dissipate my energy away. The only thing for me is build my pressure. So this criterion is pressure coupling. This criterion is make the supersonic speed. So these are the two. So if you do, and my student John, they did some kind of simulation. They basically show that the detonation, if you meet the criteria here, detonation is here, and then detonation fail is here. And then you plot this thing too on this diagram. You basically say, okay, horizontal, this epsilon criteria is almost equal to 1. And in vertical is C. You only have some region close to 1 that you can form a detonation, and otherwise you don't. But how detonation transition happening from flames to there. So that is a something, and I can share with you and later. I don't have time. So with that, you understand. So that means that ignition plays a big deal role in DDT. So then I said, okay, so why not just, I asked an undergraduate student and here, and why don't you just use plasma-generated ozone can accelerate detonation? Indeed. And the plasma and this, they can both accelerate detonation and delay detonation. I talked to you yesterday. So now you understand better why that the plasma can enhance detonation control. So this is a picture I showed you yesterday, and how plasma and accelerated detonation is so beautiful. And then you do a laser diagnostics to measure that this is a detonation DDT without plasma. You can see the formaldehyde measurement is very tiny in front of the flame. This is the flame. The formaldehyde is only in front of the flame. But with plasma discharge in the channel, you can see lots of formaldehyde formed. And then that creates a low temperature chemistry formation to form formaldehyde, accelerated ignition. Once the ignition is accelerated, the shock wave coupling with the ignition is enhanced, then accelerated detonation. So, all right, well, I try to share with you that how plasma can assist the ignition, how plasma can extend the flammable limit, how plasma can control critical radius, and how that controls detonation in terms of dynamics. And now I try to switch the gear in talking about that the plasma, I think that is the plasma chemistry should be number 5. And I skipped that the electrofield effect with flames. That is interesting, but it's more about the ionic wind effect. I think chemistry is very important. So a plasma, a combustion, and a chemistry. So we want to understand in a plasma, in combustion chemistry, there are a few things you really pay attention. One is chain branching reaction, right? It's always important, number 1. Second is that the branching ratio of key reactions, that one give you a termination, the other one give you a radical. So that branching ratio is so important, and in combustion kinetics. And in plasma is the same thing. Plasma can generate electron impact reactions for excited species, electronically, vibrationally. They also generate that fast heating and slow heating, and generate ozone, O singlet, NOx, and many other things. And then there are very short time scales they can generate. And then we really understand how that the chemistry of plasma affect combustion from an elementary kinetics point of view. So in this room, everybody understands that the chain initiation reactions are typically very slow, because you want to break down that the CH bond, and it's not easy to do that. But that the important reactions are chain branching reactions. For example, as I said, high temperature is H plus O2 reaction, generate 2 radicals. And these things only happen fast if you're above 1100 Kelvin. Now, of course, depending on pressure. And this one, that is happening between 800 to 1,000 Kelvin, 800 to 1,000 Kelvin. And this low temperature cool flame chemistry affects between 300 to 800 Kelvin. They are slower, fast, slow, slower, and depend on the temperature. And then if you have an electron impact reaction with oxygen, you generate 2 O atoms. One O atom will attract this H from fuel, generate OH. And then this low temperature chemistry, they can generate 2 OHs. So in the end, 1 O radical at a low temperature, they give you 3 OH that make the reaction faster, right? This is the plasma. And also, in other words, that the electronic excitation of oxygen for this kind of O2 singlet, they generate a reaction, H plus O2 reaction. This reaction is faster than this one. And so I have not seen any experiment and really shown this at high temperature. This remains to be seen. And even though numerical modeling is showing that, but the experiment has not been confirmed. So in many reactions in plasma, so first class is excitation. Electrons collide with a molecule. They generate vibrationally or electronically excited. And the ionization, that when electrons impact with the molecule, they can strip the electrons away by photons, by electrons. They can, this is that yesterday we talked about the Townsend regime, right? And this is attachment, that is loss. This is if electrons attach with the water, that the plasma is going to be weaker. So electron attached to oxygen, and so these are the quenching about the plasma. So a detachment, of course, is opposite. Dissociation is very important that for combustion, because they heat a molecule and break down the molecule into radicals or into fragmentation. And then you have a quenching, and you have a three-body recombination. All these mechanisms need to be considered. That make a plasma modeling is so challenging because these reactions, they are very fast. They are much faster than a combustion process. You make a simulation timescale, typically from microsecond all the way suddenly drop to nanosecond. So there may be 3 orders of magnitude, and you have more reactions too. So this is, again, I try to remind you again that the energy transfer in plasma is dependent on electron energy, is E over N. At a lower E over N, you got the vibrational, and this is strongly molecular dependent, and allow you to design a plasma to tune ignition or methane reforming or CO2 reforming. And then you have a high electron energy, you got dissociation, electronic excitation, and ionization. So these are the plasma properties. In air plasma, you can see there's a lot of electronic excited state for oxygen, nitrogen, ions, negative ions, and many intermediates. So these things need to be considered. But fortunately, not all of them are important. Only a few of them are really important. So for example, if you have a plasma, if you're looking at this energy diagram about in air and in methane, so electrons basically heat the nitrogen get electronically excited, and they dissociate oxygen into 2 atoms. And dissociate nitrogen into atoms, they form a NOx. And they also create a vibrationally excited nitrogen and dissociation. And this O atom, at low temperature, they become ozone. So this is well-known kinetics. Another way that they can electrons heat that the fuel and generate fragmentation of the fuel. So this is also well-known. A lot of people measured it and before. And the other thing that the electron, they generate oxygen, they generate O and O singular D. O singular D chemistry is fully known and in plasma. And then it also generate O singular D or molecular O singlet, and then reaction. This is also less known. So therefore, there are so many things we don't know. The fragmentation, for example, electron impact with this, nitrogen with fuel, O1D with, for example, in ammonia combustion. What is that the electronically excited nitrogen and react with ammonia? Does it become NH2? Does it become NH plus hydrogen? And I don't think that anyone really knows what it is. And O1D, for example, you have O1 singlet, reaction with ammonia. Does it become what? What is the product? See? I think once you come to this area, very little is known. When you write a proposal to DOE Basic Energy Science, they like this kind of thing because this is so many things we don't know. When you write a combustion, let's say H plus O2 reaction, and then they say, okay, we know it, but 10% uncertainty already. What do you do? And don't do anything is within a single digit uncertainty, right? There are some people better than us. Let's say NIST, for example, they are better than us to do something 0.1% or 2%. But for us, we fight innovative ideas, orders of magnitude difference, right? That's something we want to do. So this is a very interesting experiment and done by my colleagues at Chris Laux in France. And he did a nanosecond discharge, and he fired a nanosecond discharge here. And what he did, he measured that using a cavity ring down spectroscopy, and he measured that on the Talif, he measured this excited nitrogen on B and C. And they found that when the B and C decay, and they found that the oxygen is increasing. And this clearly showing the mechanism that the O is generated by nitrogen B and C. Not always B, and A could be, but this condition is nanosecond. So they created this main reaction. So now you try to understand that how that they bring you to the chemistry, high temperature, intermediate temperature, low temperature chemistry. You can see all this kind of plasma chemistry now start to couple mostly with the low temperature chemistry part. They're going to enhance low temperature reactions. And if you listen to Bill Green's talk, he will talk to you about the transition state theory, how the reaction is calculated. Nowadays, most of the reaction, I would say that probably 50% uncertainty already know for most of the combustion. But here, you probably order magnitude, we don't know. Yeah. So, for example, how this reaction rate will be and how this will be at a high temperature. So there are many things we don't know. So the plasma process, it is that they have ion molecules, electron kinetics, and the combustion process. Combustion timescale is typically long, is a microsecond to millisecond or longer. But that the ion chemistry and the electron chemistry, they are very fast. They are probably from a picosecond to nanosecond timescales. And to understand this, you need ultra-fast laser diagnostics and to really dictate what is that the dynamics, reaction kinetics. And that is the tough part about the reaction. But fortunately, that there are many things that people have been done in the plasma field, electron impact reactions. There have been a lot of study already been done in plasma physics. And they know some of the reaction rate. And there's a lot of things going down in combustion, and this, I think, they're pretty much well understood in terms of small chemistry. Ammonia probably is different because of NOx. But the most important thing is that here, that the plasma generate that the radicals, excited state, and how do they interact with fuel is poorly known, that region, right? So try to show you some examples. This is that diagram of oxygen. As I said, this is ground state. And then two of the lowest electronic excited state is O2 singlet, O2 1 sigma, O2 1 singlet, O2 1 sigma. But if you have electron energy so high, they can pump that molecule all the way to O2A state, pi state, and also sigma state. If you go to sigma state, they can dramatically create, this energy is so high, they can dramatically dissociate oxygen into O ground state plus O singlet state. So here, that if you excite the electron energy is high, higher than 8.4 eV, you are producing O and O1D. If the energy is lower, and you only produce a ground state, and this is at the oxygen. You can do similar things in terms of a nitrogen diagram. So nitrogen, you can excite it, the nitrogen A, nitrogen B, nitrogen C. So their energy is much higher. We can see the nitrogen A state is 6.2 eV, and then B is about 7 eV, and nitrogen C is 11 eV. That's why that the nitrogen B and C, they can dissociate oxygen very effectively, because more than 70% in the air is nitrogen. So these electrons will be interact with nitrogen that create electronic excited nitrogen. So this way you can see that this is a nitrogen. If you have a hydrogen and air mixtures, and you can see that the nitrogen vibration is very broad, and even at 100 Townsend, very strong electrical field, the vibrational nitrogen is still there. So therefore, vibrational nitrogen cannot be ignored, and in air plasma, and then because they are always excited there, they're coupling with other radicals, they change your reaction. And at the high electron energy, at the breakdown, and you have this a nitrogen C state, the higher state, and then you have the C state have a lot of energy. They just break down to nitrogen into oxygen into radicals. So, but this energy is much higher than this dissociate energy, what happens for the rest of the energy? The rest of the energy will become heat. So this is what happens that if you have a, for example, for hydrogen, if you excited hydrogen and to excited state, and that hydrogen and dissociate hydrogen into ground state and H1s, the extra of this energy is about 4.5 eV. You generate the electrons, dissociate it, and then these electrons, molecules, hydrogen molecules, you dissociate hydrogen molecules, they're very hot because electrons, you collide it and dissociate it is very hot because not only that they have dissociated, but also they have extra energy created. When you have a hot hydrogen, that hydrogen scattering with a hydrogen with other molecules, the cross-section areas change. So therefore, not only that they produce radicals, but they produce hot radicals. The hot radicals will change that your reactivity and the cross-section area as well. So fast heating and slow heating. As I said, plasma, they have two, not only produce radicals in excited state, but also produce heat. Some of the heat produced in nanosecond by this excited state. For example, nitrogen excited state dissociate oxygen into 2O, they generate extra energy. And excited oxygen, they dissociate, also create this. All this ion-ion recombination, that this happens in nanosecond to tens of nanosecond. And so slow heating is vibrational energy relaxation. So this is happening at a microsecond to millisecond. So if you're looking at the fraction about that energy transfer in terms of function of oxygen at a different electron number density, and you can see that if you increase oxygen, the fraction about that the fast heating is increasing. Is this indicating that these reactions, oxygen reactions, play a big deal role in fast heating, right? So when you have oxygen in the mixture of plasma, make sure that this type of fast heating mechanism is included appropriately because they are going to change your temperature, not only just produce your atomic oxygen. So plasma chemistry is that depend on the E over N, and then they can generate ions, and these ions, they can charge transfer, they form a reaction complex, and then they do generate hot atoms, as I said. They generate a lot of radicals. So eventually they accelerate low temperature chemistry, and but you don't have to consider all of them, So, and also that can generate a vibrational state. That vibrational state can, change that the reaction rate, which is slightly different from combustion. And so that gives you a new reaction channel that it typically does not exist in a combustion. And this is that the reaction we summarized before, electron impact for oxygen, electron impact, ion recombination, and all this kind of dissociation reactions, and fast heating and slow heating process in a typical and air plasma. Now I try to say, okay, so what? All these things is generated, and how does that affect my individual chemistry? So let's look at this. So here that is have an electron impact, oxygen dissociation to O and O1D. And this is that the typical reaction rate, constant. If we plot the reaction flux about this plasma chemistry versus of combustion chemistry, pay attention to this. This is a H plus O2 reaction, you can see from here. This is a dominant reaction in combustion. And around the temperature about 1100 Kelvin, when this reaction is taking off, is proceed, then they produce radicals much faster than the strongest plasma we can do at 5,000 tons. That again comes back to my conclusion. If you have very strong flame, plasma cannot compete with H plus O2 reaction in combustion by itself. But at the low temperature, and if you see that the proxy dissociation or chain initiation reactions, they are much, much slower compared to plasma. So plasma can dramatically enhance this low temperature and also that the intermediate temperature reaction rate just from the diagram. So let's compare some elementary reactions. H plus O2 reactions is important, produce two radicals. So this is the ground state, and this is the ground state reaction rate as a function of temperature. This is that if you excited oxygen into a singular delta, and this is that the reaction rate it has. And you can see that the reaction rate at a low temperature is about 2 orders of magnitude faster. See what I'm saying? This is why that is important. And here we can say the same thing, that the O2 reaction with methane, ground state is here, and O2 reaction with methane form a HO2 from methoxy. This is one of the most important chain initiation reactions. They're also faster by almost 2 orders of magnitude. And then you're looking at the CO reaction with a O2 singlet. Again, this story is similar. And then that electron impact dissociation reactions, they are very efficient, very important in plasma-assisted combustion and to dissociate oxygen. So, and now we try to see that, okay, so there are so many important reactions. This is the combustion, this is the O singlet. They are 2 orders of magnitude as, this is that the important reactions in combustion. This is that the O singular D reaction. You can see, even at a lower temperature, they are almost the orders of magnitude higher. So creating this O singular D reaction with fuel is very important. But very few experiments that measure this O singular D. For example, you have O singular D reaction methanol, and then one of the product is methyl hydroperoxide, and then so what is that the reaction channel from here to here and here to here, and then particularly for methanol. So we know that when O1D reacts with ethanol, this 55% goes this way, and 45% goes that way. What about for DME? And nobody measured it. And we just have a paper accepted at JPC letters, and we measure this data. I found that many of our experimental data now is on the LIST database. And we measure this reaction rate. We'll show you what it is. So we can measure it. Alcohol with O1D, they have many, many channels. We can measure that the products of OH, measure that HO2 formation from this intermediate species. You can fit that experimental data back to the OH and HO2 signal. We determined that the branching ratio of this reaction is 44% here, is 42%. Many of the reaction here does not exist in combustion because this O atom is directly inserted into the CH bond and form this product. And this is very important. You make a methanol radical, which is very reactive, and methoxy is also reactive. So that's why I'm saying that the branching ratio of these reactions are so important to affecting reactivity, which you have in situ diagnostics. We also did this with a collaboration with the University of Minnesota, Dan Chuler's group. They calculated this O1D reaction with DME. And they found that this reaction channel here to form a methoxy is very important. And we did the experiment and measured that the OH formation and HO2 formation. We found that the methoxy is 90% at 30 tau, 76% in 60 tau, and then different. So, and this gives you a lot of opportunity. You can do something that people are not. I bet this reaction rate will be, captured to NIST database very soon, and people will be shared with the community. So this, I talked about this, about how ozone reaction with them. And Niels Hansen at Sandia, they did a lot of measurement. They measure a lot of hydroperoxide formation at a low temperature, and ethanol and ketone formation in this chemistry. And they really provide a quantitative data to help to understand how this reaction channel is going on. We need more people to do that. For plasma, you also have this NOx formation, as I said. They can delay that the low temperature ignition, but dramatically accelerate in the middle temperature. So the NOx plasma generated NOx coupling with a low temperature chemistry is very important and need to be understood and as well. So if you make that the NO in air, you make a lot of NO in the air. But if you mix that the air with a 1% endodecane, and you found that the NO is decreased dramatically. And where is NO gone? NO mostly becomes to, when you say, oh, NO mostly becomes to a reactor with a few radicals, they become NO2. So that's why you don't see NO. Does not mean that NO is not there. NOx is still there. And the Wen-Ting found that they did a wonderful experiment to show that the plasma-assisted ammonia combustion, as I said yesterday, they dramatically reduced NOx. That's because probably that the NH2 reaction with NO, that reduced that NO formation. So, and recently to understand the plasma ammonia oxidation, we set up an experiment in the lab with this Harrod cell with a DVD plasma discharge, and this is the ICOS that we can detect NO2, and that way laser absorption can measure N2O and water and OH radicals. And we find that we put the plasma chemistry with ammonia vibrational states and oxygen and nitrogen electronic excited state and ions, and we conduct the simulation. So this is that original model, and they don't predict that the N2O formation. And this is that the updated model by including that electronic state about nitrogen electronic state in reaction with ammonia. So you can fit that the curve and much better than the model can prediction. So what you can see is that ammonia, when you see plasma, they can break down the plasma into NH2 and NH and very efficiently, and depending on what kind of states you are using. At the same time, the plasma can react with oxygen and with nitrogen. They've created this kind of O and N atoms, and they couple together to form HNO to NO formation, and then they promote that the NO2 formation. But also that can reburn it, and the NH2 formation with NO, it can reduce to N2, and the same is here. So plasma maybe provide a good opportunity to enhance combustion of ammonia, and also that reduce the NOx by this kind of reburning reactions. So we need more experimental data in this area, and then try to provide a validation target. So this is something I want to talk to you today about the chemistry, what we have done in last 10 years. And now the next thing we try to show you is that the diagnostics. So diagnostics is the key, and in plasma. And without diagnostic, we really don't understand, because the plasma process is so fast. And so I talk about the diagnostics, and then talk about a little bit of instability, and when I have time. And then we go to numerical modeling tomorrow, and then electrified manufacturing tomorrow. What is time right now? So I don't. It should be to 11 or to 11, right? What? 5 minutes, right? Correct? Okay. Okay. All right. So let me get started. 5 minutes. 5 minutes. And if you're looking at plasma, so you got a lot of electrons, electron temperature, electron energy distribution function is very important. This is non-Boltzmann, so they affect your reactivity. And you have gas molecules, a lot of ions radicals, excited state. And you want to measure this in order to say, oh, my model can predict it, or my model can fail it. So this gives you additional challenge compared to combustion. But combustion people has been well funded in the last 20 years, and to develop all fast diagnostics, which is really beneficial to plasma area. So when you're really looking at plasma areas, plasma people, normally they do it using emission spectroscopy. but the quantitative measurement about combustion people and bring the techniques to the plasma field really help them to understand something better. So the first thing is that how do we measure electron number density and electron temperature? So this is something that is well known in the literature and using Thomson scattering. That is an elastic scattering if you have a photon laser coming in this direction, if we have charged particles, and they will scattering and depend on the angle and on the polarized plane and on the scattering plane. So this scattering is a function about this where that the scattering angle will be and which observation angle phi will be. So, and then the number of photons of electrons for the electron generated in scattering is proportional to the strength of electrical field and proportional to the length of that the volume for diagnostics and proportional to the number density, and this is that the cross-section area and integral, and then that is the optical efficiency. So if you collect that Thomson scattering together with Raman scattering, so you take a ratio of it, it can cancel many of these things. So by taking a ratio about that the electron number density, we are proportional to the signal of Thomson scattering, normalized by Raman scattering, with the Raman scattering cross-section area, which you know, and the cross-section area of Thomson scattering. So with the number density of nitrogen, you know, with that the fraction of nitrogen molecules in excited state, J equals 6 or 7. So then you can see that everything here is measured, and everything here you know, and you know this vibration. So you can calculate the electron number density. But at the same time, that because electrons, when you collect the signal, this signal is affected by Doppler broadening because electrons are moving very fast. When they're moving very fast, that the spectrum about this Thomson scattering is broadened. And using that broadening, you can see the broadening is a function about the speed of electrons, which is square root of electron temperature. And then you can say, by measuring that broadening, you can say, oh, my electron temperature can be, depending on the broadening, about that the scattering. So in this experiment, you can measure two, electron number density, electron temperature. So I'll show you that this experiment my grad student, Tim Chen, set up. So this is a very similar to the Rayleigh scattering. So you have a Yak laser and at 532, and you reflect it, you pick a Brewster window to reduce that the reflection, and you come into the plasma discharge, and you collect that the Thomson scattering, you put it in the spectrometer, and you connect to ICCD, and you collect the signal. So here's the result. So this is that the Raman scattering, and this is that the Raman scattering together with Thomson scattering. If you subtract them, this is that Thomson scattering. So this is the area is blocked by that by the objective, and this is that the width of this Thomson scattering can allow you to do the electron temperature, and this area under this curve, and they give you that the intensity about the Thomson scattering, and they give you a number density. So here that is the measurement about the Thomson scattering measurement of argon as a function of time. You can delay that the laser and in a nanosecond time scale allow you to electron number density as a function of time. You can see that the electron number density build up. You can electron temperature after the plasma discharge, quickly going down to about half of electron volt, 5,000 degree and 6,000 degree in that level. So this gives you a quantitative result. So let's do that one, compare with the experiment. This is that number density and electrons in a methane. So we measure the electron number density, we measure the electron temperature, we computationally model it. But you can see that here that is a helium and without a methane. And here the 1% methane, 2% methane. You can see that without methane is here with 1% and 2%. 1% and 2% almost the same. So, but 0 to 1 is significant. So this is contradictory to previous plasma people. Plasma people always think that you're adding some kind of a reactant, methane, ammonia, into the mixture, that the electron temperature is linearly affected. But our experiment basically show that no, it's not linearly affected. It is that it is non-linearly affected. So that is a dramatic change in terms of UV. Just like that, you put some kind of hydrogen into methane, the ignition delta time is not linearly change. It's non-linear change. Is that because that the plasma chemistry? The flame speed maybe is linearly, but So this is that the experiment about Thomson scattering made by Yiguang and Movich at Ohio State, and this you can clearly see. This is that the Thomson scattering, and this is that using the width you can measure the electron temperature about 2 EVs, and this is electron number density very high, is about 150 ppm. So this is that the needle to a sphere. They have a sphere. There's a needle. You can see this discharge. So that measure. Again, that if you change it into a oxygen, and then you can measure that the electron temperature, and then in an oxygen environment, you found that the electron number density and the electron temperature goes down. So in hydrogen, if you want to do ammonia synthesis, you often put a nitrogen and hydrogen into it. You found that when you're adding hydrogen, the electron number density increasing, and electron temperature is increasing. And when you put oxygen into it, the electron temperature is decreasing. So therefore, that plasma is very sensitive to the reactant you put. So that gives us a wonderful opportunity to understand electrified manufacturing. How do we make methanol from CO2 and hydrogen? How can we make ammonia from nitrogen and hydrogen? Using plasma. All you need to understand is this. That gives us tremendous opportunities, advantage that other people, they don't understand that detail. Because we come from combustion side, we have a much better understanding about the kinetics and the importance as well. So the next thing, try to measure electric field, because electric field dictate your electron temperature. So people are using a second harmonic generation. Typically, that a molecule like nitrogen, you don't have a second harmonic. But if you have a femtosecond laser, a picosecond laser, their electric field is so strong, they can break down the symmetry of the molecules. At that time, we put the electric field there, and that also, oscillation frequency is going to be dependent on your electric field when you have a polarized. So therefore, by doing the second harmonics, and you can see my signal about the second harmonic is proportional to the square of the number density and to that square applied field, and then that is the energy of the laser, applied lasers. So this is a very, you fit that the signal as a function of electric field. You start to see that indeed the signal is, a square quadruple dependent on this field. By doing that, you can set up very experimentally pretty simple. You just need a very strong and a laser, and that maybe is a picosecond laser or femtosecond laser, generate a very strong electric field to break down symmetry of the molecular, and you put an electrical field here, the DVD discharge, for example. The second harmonic generation can be separated from original beam, and you can collect it. So that is give you can see this is that the electric voltage as a function of time. It's applied field. This is a measured field. Applied field, you using that voltage divided by the gap. This is what you have. But when you measure it, you can say, okay, initially before the breakdown, everything is the same. After the breakdown, that the measured electric field is quickly almost going to zero compared to the applied field. Why do they quickly go to zero? After the breakdown? This is yesterday we talked about this Debye length. See what I'm saying? Before breakdown, that you don't have electrons, don't have enough ions, so electric field is there. After you break down, you generate a lot of electrons and ions, and then the electron and ion quickly move and shield that your effect of electric field. See what I'm saying? So only the electric field now exists near the cathode and anode. There's no electric field between after breakdown. This is that the shield effect of by plasma, right? This is the interesting. different from combustion. So now we can measure that these, in argon, we can measure how the electron number density and how the electric field at the same time, and how that electron temperature change as a function of field. So now you got two parameters that you can model this thing in a quantitatively, so that you can see whether your plasma model can do something. And then another thing is that plasma often change very fast. For example, the radio frequency plasma, they are typically at 100 megahertz. So you need to measure something is at a nanosecond. So here I give a radio frequency waveform, and I try to measure that the change of electric field, and in this a high frequency. I'm not sure that you can see this video. You can see Tim Chen, my student Tim Chen, and he measured that the electric field frequency at a few nanosecond timescales by delay the optical beam. So now we got a lot of good techniques, and from combustion side, they can not only detect electron number density, electron temperature, but electric field, but also can detect transient variation of electric field. This is so important. If you can do this fast, you can detect the streamers move forward. You can detect how fast the streamers head, the electric field in streamer head. That is very critical data for plasma. So Yiguang Adamovich, again, my collaborator at Ohio State, and he tried to measure two-dimensional distribution about the electric field. And this is a knife edge, and some of you may use it. And this is at the dielectric, it's a dielectric plant. And you can see he put a knife edge, he put a dielectric field. We fire a nanosecond plasma like this. You want to measure, this is the voltage, it's the current, this is the energy. You want to measure what is the electric field. So if you're looking at from the side view, you can see this is at the rod. The plasma hits the surface and spread on the surface. And here, that is the front view, you can see that their plasma is charged and like a curtain. And if you're from the top, you can see the plasma hits the surface and spread on the other side. See what I'm saying? So this is very interesting. People really want to understand what is the electric field, what is the Lambda density, and what is electron temperature, so that they can model it. So this is what I try to to show you his result. Is we can show you that this is that the voltage swing. This is that the electrical field. This is that the absolute field. This is a negative field. So you can see that when there is a voltage apply, and electric field start going up, after breakdown, the electric field going down. But suddenly the electric field become reversed when the voltage is still going down. That means a lot of charges is building up on the surface. They create reverse electric field, right? If you don't measure it, you don't even know these things are happening. This is typically very important for silicon manufacturing. If it was an ion beam, you try to cut the silicon, but you find the ion is building up on your surface, and is affecting your next ion coming in. That is dramatically hurting your accuracy, whether it's 2 nanometers or whether it's 1 nanometer. See what I'm saying? So it's very important to measure this electric field. And he measured X, Y directional electric field, and then make it, take a square root of them together, what is the absolute electric field. So I try to show you that today that technology becomes so advanced that we can measure electric field and number density. The other thing that in the old days, people want to measure emissions. For example, with argon. The argon is ground state is here. And so if you have one electrons that excited to S state, or one electrons jump to the P state, P orbital, S orbital and P orbital, then you create many of new states and here. So you can using the emissions from that one of the excited state, 1P1, and then or emission from the other state, and you can tell what is that the electron temperature that create this excited state. So, and this is that the experiment at the Tsinghua University by Yiguang, who graduated from MIT. And he basically saying that I have a plasma, needle-to-needle plasma, and I have a ICCD camera, and I want to watch that in hydrogen and argon mixture. I want to see the emissions, and using that emissions to estimate that the electron number density and things. But you want to use emissions to estimate it, what do you need? You need to actually measure the emission. And second, what do you need? You need a kinetic model. Otherwise, how do you know the emission is coupled with number density and temperature? So that model has to be correct. Otherwise, so that's why they only can do for hydrogen and argon. If you're adding a little bit of methane, completely screwed. So this kind of emission spectroscopy. So this is what they do. They are using that argon emission spectroscopy, using a hydrogen alpha line and a beta line, and to feed the electron number density. But you can see here the uncertainties. The uncertainty jump huge when the number density is 10 to minus 14. Most of the weak ionized plasma in my laboratory, the electric barrier discharge, electron number density is around here. So your electron number density cannot do anything. So the only can see doing is arc, like gliding arc can do it. So when you pick up a diagnostic method, you want to make sure and what is the hypothesis, what they can do, what they cannot do. And don't jump in, spend a lot of time doing this. In the end, you find, oh, it does not work, right? So, okay, maybe take a break, some of you. I just